Welcome to this video. Today, we'll be tackling an interesting problem titled Binary Search Tree to Greater Some Tree. In this problem, we'll explore how to transform a binary search tree such that each node's value becomes the sum of all values greater than or equal to itself in the tree. Let's dive in. In this problem, we are tasked with converting a binary search tree, or BST, into a greater some tree, or GST. The goal is to modify the tree so that every node's value is replaced by the sum of all values in the tree that are greater than or equal to the current node's value. To understand this, let's quickly recap the structure of a BST. In a BST, each node has a maximum of 2 children. For any given node, all the values in its left subtree are smaller than the node's value, and all the values in its right subtree are larger. This property is key to solving the problem. The function you will implement takes in a single input, the root node of the BST, which serves as the starting point for the transformation. The output of the function is the root of the modified BST, now transformed into a greater some tree. Let's take a look at an example to better understand the problem. The input here is a BST represented as an array, 4 1 6 0 2 5 7 null 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 3 null 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 8. The tree structure before the transformation looks like this. The root node has a value of 4, with 1 as its left child and 6 as its right child. The left subtree of 1 includes 0 and 2, and the right subtree of 6 includes 5 and 7, with 7 having an additional child, 8. After applying the transformation, the output array becomes 30 36 21 36 35 26 15 null 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 33 null 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 8. If we visualize the tree after transformation, the root node now holds the value 30, while all other nodes have been updated to reflect the cumulative sums of all keys greater than or equal to their original values. This transformation preserves the BST structure while updating the node values. Now, let's break down how the transformation happens. The key is to calculate the cumulative sum of all values greater than or equal to each node, starting from the largest value in the tree. For example, starting with the node containing 8, there are no greater values, so it remains 8. Next, the node with value 7 gets updated to 7 plus 8, which equals 15. The node with value 6 then adds 6 plus 15, resulting in 21, and this process continues for the rest of the nodes. This cumulative sum is typically calculated using a reverse in-order traversal, where we process the right subtree first, then the current node, and finally the left subtree. This ensures that we always process the larger values before the smaller ones, which aligns with the problem requirements. For clarity, let's also consider a second example with a simpler tree structure. In this second example, the input tree is represented as 0, null 1. The tree structure before the transformation is straightforward. The root node has a value of 0, and it has a right child with the value 1. After the transformation, the output becomes 1, null 1. The updated tree reflects the cumulative sum of values, starting from the largest. For the node with value 1, there are no greater values, so it remains 1. For the root node with value 0, we calculate 0 plus 1, which results in 1. This example demonstrates how the transformation works even in smaller or less balanced trees. Finally, let's discuss some constraints and edge cases to consider. The number of nodes in the tree ranges from 1 to 100, and all node values are non-negative integers, with a maximum value of 10,000. Additionally, all node values are unique, and the input tree is guaranteed to be a valid BST. For edge cases, consider a single node tree, where the transformation doesn't change the node's value since there are no other values to sum. For a right-skewed tree, where each node has only a right child, the transformation operates like a cumulative sum from the largest to the smallest value. In contrast, a left-skewed tree, where each node has only a left child, requires summing greater values without processing a right subtree. Lastly, nodes with the maximum value in the tree remain unchanged, as there are no values greater than theirs. These cases highlight the flexibility of the transformation process across different tree structures. To solve the problem of converting a binary search tree to a greater some tree, one initial approach we could consider is a brute force method. The intuition behind this is straightforward. For each node in the tree, calculate the sum of all nodes that have values greater than or equal to the current node. This can be achieved by performing an in-order traversal of the tree to gather all the node values in sorted order, and then for each node, scanning the list to compute the required sum. Once the sum is calculated, the node's value is updated accordingly. However, this approach is computationally expensive. Since we might scan the entire list of nodes for each individual node, the time complexity becomes n squared, where n is the number of nodes in the tree. Additionally, we need extra space to store the values of all nodes in a list, leading to a space complexity of n. Given its inefficiency and high overhead, this brute force approach is not ideal, especially for larger trees. A more efficient solution is to use reverse in-order traversal, which processes the nodes in descending order of their values. The intuition here leverages the BST property. In a reverse in-order traversal, we visit nodes in the order of right subtree, root, and then left subtree. By maintaining a running sum as we traverse the tree, we can dynamically calculate the greater sums and update each node's value directly, without requiring additional data structures. This process starts by initializing the running sum to 0. As we traverse the right subtree, we add each node's value to the running sum and update the node's value with the current sum. Then, we continue to the left subtree. Since we are modifying the tree in place and visiting each node only once, this approach is both time efficient and space efficient. The optimized approach has a time complexity of n, as each node in the tree is visited exactly once during the traversal. The space complexity is h, where h is the height of the tree, due to the stack space used in the recursive implementation. This makes the reverse in-order traversal strategy the optimal choice for this problem. By visiting nodes in descending order and maintaining a running sum, we achieve efficiency and simplicity. Additionally, this method modifies the tree directly, eliminating the need for extra space to store intermediate values. While recursion is straightforward to implement, it does come with a trade-off. The recursive call stack can grow up to the height of the tree, which might be problematic for very deep trees. In such cases, an iterative implementation could be used to reduce the space complexity to 1, though it would come at the cost of added complexity in the code. Compared to the brute force method, which is computationally expensive and requires additional memory, the reverse in-order traversal is clearly superior. In conclusion, the reverse in-order traversal is the most efficient and natural solution to transform a binary search tree into a greater sum tree. By leveraging the inherent properties of the BST, we can minimize both time and space overhead, ensuring that the algorithm is optimal for practical use. This method stands out for its simplicity and effectiveness, directly modifying the tree in place and visiting each node exactly once. It avoids the inefficiencies of the brute force approach, making it the clear choice for tackling this problem. In this problem, we are tasked with transforming a binary search tree, or BST, into a greater sum tree, or GST. The objective is to modify each node in the tree such that its value becomes the sum of all nodes in the BST that are greater than or equal to its original value. This can be achieved in multiple ways, one of which is the brute force approach. First, we traverse the tree using an in-order traversal, which processes nodes in ascending order of their values. This traversal gives us a sorted list of the node values. For example, in a BST with nodes 5, 3, 8, 2, and 4, the in-order traversal yields the sorted list 2, 3, 4, 5, 8. Once we have this list, we can calculate the sum of all values greater than or equal to each node. This can be done by either iterating through nested loops or by pre-computing cumulative sums from right to left. For instance, the cumulative sums for the list 2, 3, 4, 5, 8 would be calculated as 22, 20, 17, 13, and 8. Finally, we perform another in-order traversal of the tree to replace each node's value with the corresponding sum from the pre-computed list. While effective, this brute force approach is not efficient due to its multiple traversals of the tree and reliance on additional data structures. To address the inefficiencies of the brute force approach, we can use an optimized method based on reverse in-order traversal. The intuition behind this approach is that we can calculate the new values for the nodes during a single traversal of the tree. By performing a reverse in-order traversal where we visit the right subtree, then the root, and finally the left subtree, we ensure that we process the larger values first. This allows us to maintain a running cumulative sum as we traverse the tree. To implement this, we initialize a variable current_sum to 0, which will keep track of the running total of all the greater or equal values encountered so far. During the traversal, we first visit the right subtree to process the larger values, then update the current node's value by adding its original value to current_sum. After this, we update current_sum with the new value of the current node. Finally, we proceed to visit the left subtree, which contains smaller values. This approach ensures that each node is updated in a single pass through the tree, eliminating the need for additional traversals or external data structures. During the reverse-in-order traversal, each node undergoes two key operations. First, the node's original value is added to the current_sum, which represents the cumulative sum of all greater or equal values processed so far. Second, the node's value is replaced with the updated current_sum. This ensures that the node now holds the correct value for the greater sum tree. The algorithm also includes a base case to handle null nodes, which simply returns without performing any operations. This is particularly important for leaf nodes or an empty tree. In terms of complexity, the time complexity is O(n), where n is the number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack used during traversal. This makes the algorithm efficient both in terms of time and space. By using a reverse-in-order traversal, we are able to process the largest values first, naturally accumulating the sum as we go. This eliminates the need for external data structures and ensures the approach remains space-efficient. Additionally, this optimized approach handles various edge cases seamlessly. For instance, in a single-node tree, the value of the node remains unchanged, since there are no greater values to consider. For an empty tree, no action is required, and the algorithm simply exits without making any modifications. In the case of a skewed tree, where all nodes are in a single branch, the algorithm still operates efficiently due to its O(n) traversal. It's also worth noting that the BST structure is preserved throughout the process, as we are only modifying the node values and not their positions. The recursive stack used during traversal ensures that the space complexity remains proportional to the height of the tree, making it highly efficient. Now, let's take a look at a concrete example to see how this algorithm transforms a BST into a greater sum tree. Consider the input tree with the structure 5 as the root, with 3 and 8 as its children, and 2 and 4 as the left and right children of 3, respectively. We'll walk through the transformation step by step. To transform the given BST into a greater sum tree, we start with current_sum initialized to 0. First, we traverse the right subtree, beginning with node 8. Adding its value to current_sum, we get current_sum equals 8, and we update node 8's value to 8. Next, we process the root node 5. Adding its value to current_sum, we calculate current_sum equals 13, and we update node 5's value to 13. Moving to the left subtree, we start with node 4. Adding its value to current_sum, we get current_sum equals 17, and we update node 4's value to 17. Then, we process node 3. Adding its value to current_sum, we calculate current_sum equals 20, and we update node 3's value to 20. Finally, we visit node 2. Adding its value to current_sum, we get current_sum equals 22, and we update node 2's value to 22. The resulting tree now has the structure 13 as the root, with 20 and 8 as its children, and 22 and 17 as the left and right children of 20, respectively. This transformed tree satisfies the greater sum tree property, where each node's value represents the sum of all greater or equal values in the original BST. Here, we start by defining the structure for a binary tree node using the treeNode class. Each node has a value, as well as optional left and right child nodes. Then, in the solution class, we implement the method BST to GST, which converts a binary search tree into a greater sum tree. The core of this solution lies in the helper function reverse_in_order. This function performs a reverse-in-order traversal, meaning it processes the right subtree first, then the current node, and finally the left subtree. By traversing in this order, we ensure that we visit nodes in descending order of their values. The function takes two parameters, the current node and an accumulated sum. If the node is null, it simply returns the accumulated sum. Otherwise, it recursively processes the right subtree, passing along the accumulated sum. Once the right subtree is processed, we update the current node's value by adding the accumulated sum to it. Then, the accumulated sum is updated to reflect the new value of the current node. Finally, the function processes the left subtree, ensuring all nodes in the tree are updated appropriately. Once the reverse in-order traversal is complete, we return the root of the modified tree. This ensures that the entire tree has been successfully transformed into a greater sum tree, where each node's value now represents the sum of all values greater than or equal to it in the original tree. This approach modifies the tree in place, making it efficient in both time and space complexity for this type of problem. Here, we start by defining the structure of a binary tree node through the treeNode class. Each node contains an integer value, a reference to its left child, and a reference to its right child. There are three constructors provided, one with no arguments, one that initializes only the value, and another that initializes the value along with the left and right child nodes. After defining the treeNode class, we move to the solution class, where the main logic for converting the binary search tree to a greater sum tree is implemented. The BST to GST method accepts the root of the binary tree as input. Inside this method, we use a helper function, reverse in order, which performs a reverse in order traversal to accumulate and update the node values. Once the transformation is complete, the updated root node is returned. The reverse in order method is a recursive helper function that takes a tree node and the accumulated sum as arguments. The first step in this function is to check if the current node is null. If it is, we simply return the accumulated sum. Next, we traverse the right subtree first, which ensures that we visit nodes in descending order of their values. After traversing the right subtree, we update the current node's value by adding the accumulated sum to it. Then, we update the accumulated sum to the new value of the current node. Finally, we move to the left subtree, continuing the reverse in order traversal. This recursive mechanism ensures that each node's value is transformed into its greater sum tree equivalent, and the entire tree is processed efficiently. To solve the problem of converting a binary search tree into a greater sum tree, we use a reverse in order traversal. Let's start with a simple example. The given BST has the root node 4, with 1 as its left child and 6 as its right child. We begin our traversal at the root with an accumulated sum, ACC_sum, initialized to 0. First, we move to the right subtree, reaching node 6. At node 6, we attempt to go further right, but since there's no right child, we return the accumulated sum, which remains 0. Now, at node 6, we update its value by adding the accumulated sum to its current value, 6 plus 0 equals 6. We then update the accumulated sum to 6 and proceed to traverse the left subtree of node 6. Again, there's no left child, so we return the accumulated sum, which is still 6. Back at the root node 4, we continue the process. At node 4, we update its value by adding the accumulated sum, 4 plus 6 equals 10. This makes the new value of the root 10. We then update the accumulated sum to 10 and move to the left subtree, reaching node 1. At node 1, we first attempt to traverse right, but since there's no right child, we return the accumulated sum of 10. At this point, we update the value of node 1 to 1 plus 10 equals 11. The accumulated sum is updated to 11, and we proceed to traverse the left subtree of node 1. Since there's no left child, we return the accumulated sum of 11. The transformation is now complete, and the resulting tree is 10 as the root, with 11 as its left child and 6 as its right child. Next, we examine a more complex example to reinforce the process. Now let's look at a larger BST. The root is 5, with 3 and 8 as its left and right children, respectively. Node 3 also has two children, 2 and 4. Starting at the root with ACC_sum equals 0, we move to the right subtree, reaching node 8. At node 8, we attempt to traverse further right, but since there's no right child, we return an accumulated sum of 0. At node 8, we update its value to 8 plus 0 equals 8 and then update the accumulated sum to 8. We proceed to the left subtree of node 8, but there's no left child, so we return the accumulated sum of 8. Returning to the root, node 5, we update its value to 5 plus 8 equals 13 and adjust the accumulated sum to 13. We then traverse to the left subtree, reaching node 3. From node 3, we move to the right subtree, reaching node 4. At node 4, we first attempt to traverse right, but there's no right child, so we return the accumulated sum of 13. Back at node 4, we update its value to 4 plus 13 equals 17 and then update the accumulated sum to 17. We attempt to traverse the left subtree of node 4, but there's no left child, so we return the accumulated sum of 17. Now, back at node 3, we update its value to 3 plus 17 equals 20 and update the accumulated sum to 20. Moving to the left subtree of node 3, we reach node 2. At node 2, we first attempt to traverse right, but there's no right child, so we return the accumulated sum of 20. At node 2, we update its value to 2 plus 20 equals 22 and adjust the accumulated sum to 22. Finally, we attempt to traverse the left subtree of node 2, but there's no left child, so we return the accumulated sum of 22. The transformed tree is complete, with 13 at the root, 20 and 8 as its left and right children, and 22 and 17 as the children of node 20. Let's consider a simpler example with a single node tree. The BST contains just the root node with a value of 1. Starting with ACC_sum equals 0, we first attempt to traverse the right subtree, but since there's no right child, we return the accumulated sum of 0. Back at the root node, we update its value by adding the accumulated sum, 1 plus 0 equals 1. We then update the accumulated sum to 1. Next, we attempt to traverse the left subtree of the root, but since there's no left child, we return the accumulated sum of 1. The transformation is now complete, and the tree remains as a single node with the value 1. This example demonstrates that the algorithm works seamlessly even for the smallest trees. In each of these examples, we followed the principle of reverse in-order traversal, which processes nodes in the order of right, root, and left. This ensures that we visit nodes in descending order of their values. By accumulating the sum of all previously visited nodes and updating each node's value during traversal, we transform the BST into a greater sum tree. This approach guarantees correctness and meets the problem's requirements, regardless of the tree size or structure. The time complexity of this solution is O(n), where n represents the number of nodes in the binary search tree. This efficiency is achieved because the reverse_n_order function performs a reverse in-order traversal, which guarantees that each node is visited exactly once. During each visit, the operations performed are simple and constant in time, reading the node's value, adding the accumulated sum to it, and updating the accumulated sum. Since these O(1) operations are performed for each of the n nodes, the total time complexity becomes O(n) multiplied by O(1), which simplifies to O(n). This O(n) time complexity applies consistently, regardless of the tree's structure. For example, in the best case, where the tree is balanced, all nodes are still visited during the traversal. In the worst case, such as a highly unbalanced tree resembling a linked list, the traversal still processes all nodes. So, whether the tree is balanced or skewed, the time complexity remains O(n). Moving on to space complexity, it is primarily determined by the recursion stack used during the reverse in-order traversal. In a balanced binary search tree, the height of the tree is approximately log n, making the recursion depth log n. Conversely, in a skewed or unbalanced tree, the height becomes O(n), and so does the recursion depth. Combining these observations, the space complexity is log n in the best case and O(n) in the worst case. The memory usage is dominated by the recursion stack, which can go as deep as the height of the tree, denoted as OH. Importantly, no additional data structures are required, so any extra space usage beyond the recursion stack is negligible. Comparing this optimized approach to a brute force method highlights its benefits. A naive solution might involve flattening the BST into a sorted array, iterating backward through the array to compute greater sums, and then reconstructing the tree. While this would also have O(n) time complexity, it would require an additional O(n) space for the array, making it less space efficient. The optimized solution directly modifies the tree during traversal, maintaining O(n) time complexity while minimizing space usage. To formally prove the solution's big O efficiency, consider that each node is visited exactly once during the reverse in-order traversal, and each visit involves constant time operations. This means the total time is O(1) per node multiplied by n nodes, resulting in O(n). For space, the recursion stack depth directly depends on the height of the tree, O, log, n, for balanced trees and O, n, for skewed trees. This mathematical analysis confirms that the solution is both time and space efficient, making it well suited for converting a binary search tree into a greater sum tree. When solving this problem, it's important to avoid some common mistakes that can lead to inefficiencies or incorrect results. One frequent issue is using an inefficient traversal method, such as performing nested traversals or recalculating sums for each node individually. This approach introduces redundant computations, especially in larger trees, and results in an O(n squared) time complexity. Instead, you should use a reverse in-order traversal, which allows you to accumulate sums efficiently without recomputing. Another mistake to watch for is mishandling the base cases in recursion. For example, forgetting to handle null nodes or improperly initializing the carry sum can lead to runtime errors or incorrect results, particularly for edge cases like an empty tree. Always ensure you include a base case check, such as if root is none, and properly initialize all necessary variables. Additionally, relying on global variables to store state across recursion can be problematic. Global variables may not reset between test cases, leading to bugs in environments where multiple cases are tested. To avoid this, encapsulate state within helper functions or use function arguments to manage it effectively. Now, another critical issue to address is the failure to handle edge cases. This includes scenarios like single-node trees, highly unbalanced trees, or trees with negative values. Overlooking these can cause incorrect outputs or missed corner cases, which is especially problematic in an interview setting. To ensure your solution is robust, test it against a wide range of edge cases before considering it complete. Overcomplicating the logic is another common pitfall. For instance, manually tracking visited nodes or using auxiliary data structures unnecessarily can make your code harder to debug and maintain, and may introduce subtle bugs. Instead, aim for clean and concise logic that leverages the inherent properties of binary search trees, such as the natural sequence provided by in-order traversal. Simplifying your approach not only improves readability but also reduces the likelihood of errors. In interviews, there are several key points to keep in mind for this problem. First, recognize that reverse in-order traversal is the optimal approach for operations requiring cumulative sums in a BST. This traversal processes nodes from largest to smallest, making it straightforward to accumulate values as you go. Be prepared to discuss the trade-offs between recursive and iterative solutions. Recursive solutions are often more concise and easier to write, but they come with the risk of stack overflow in cases of very deep trees. Iterative solutions, on the other hand, avoid recursion limits but require careful management of an explicit stack. It's important to communicate how you're handling edge cases during your explanation. For example, mention how your solution accounts for null nodes, trees with negative values, or duplicate nodes. If you start with a brute force solution, demonstrate your ability to quickly identify inefficiencies and transition to an optimized approach. This shows interviewers that you're capable of refining your solution under time constraints. Lastly, this problem has strong connections to others, such as convert BST to greater tree, which is almost identical in approach, and KTH smallest element in a BST, which focuses on in-order traversal. Recognizing these relationships can help you build a deeper understanding of BST problems. Finally, let's consider some alternative approaches to solving this problem. The most efficient method is reverse in-order traversal, which has a time complexity of O(n). This approach directly leverages the structure of the BST, but it does require a solid understanding of traversal patterns. Another option is a brute force approach, which involves recalculating sums for each node. While simple to implement, this method is highly inefficient with a time complexity of O(n squared), making it unsuitable for larger inputs. For those concerned about recursion limits, an iterative approach using a stack is a good alternative. It also achieves O(n) complexity but requires careful stack management to ensure correctness. Each of these methods has its own trade-offs, so understanding their strengths and weaknesses will help you choose the best approach based on the problem requirements and constraints. Great job following along. We've transformed a binary search tree into a greater sum tree using an efficient traversal method. Remember, mastering tree traversal techniques is key to solving many tree-related problems. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!